in time, it's not clear why things were the way they were. And of course, we're not satisfied with just saying because they were. We want to go and explore that some. So inflation actually helps with the horizon problem. This is actually a space-time diagram. So you can look at this as time running forward or up here, and space running left and right and back and forth. And these cones represent, the surface of these cones represent, of course, the path of light. And in this case, all the expansion of the universe has been sort of taken out of the picture to give you sort of a heuristic feel. But the point is, our two sides of the sky that we observe with our satellite up here, one side will be looking at this part of the cosmic microwave background, one part would be looking at this one. Their light cones never intersect, which means they never were able to get in thermal contact with each other and arrive at the same temperature. Inflation provides a mechanism that basically extends the history of the universe, albeit in a condensed amount of time, so that those light cones do intersect, and it does allow those parts of the sky to be at the same temperature. The flatness is maybe a little bit more obvious. Essentially what happens is if you inflate any geometry large enough, if it has an initial curvature, it looks flat, right? If you blow up the surface of a ball large enough and you look at a small enough area, it's nice and flat. And this is something that inflation had a lot of, being able to multiply the universe's geometry by a factor of 10 to the 30 in a short amount of time. The expansion problem, well, inflation pushes the universe apart. That picks that as opposed to collapsing. And structure, well, inflation actually allows a mechanism for quantum fluctuations to actually be blown up to cosmological sizes and thereby produce this anisotropy that we see. So I like this slide because I think it also captures everything that I just said, and maybe I could have shortened the talk by 30 minutes or so. But again, we're looking at time going to the right and space being up and down and in and out of the board here, or the screen here. And so the history of the universe is such that you basically have this tiny little universe that we start off with. Inflation blows that up to current cosmological size. You have a series of phase transitions or changes in the universe where we start to slowly look like, well, not that slowly, but start to look more like the physics we see today. Physics changes as you go lower in temperature. Finally, you produce the cosmic microwave background, the universe becomes transparent, and then doesn't do much for a while. We have this period of dark ages here, where what's going on there, as I said before, was you've got these tiny density perturbations. They're drawing in matter and energy, stealing it from the less dense areas. Eventually, after about 400 million years, they do that well enough to turn on the first stars, which ionize the universe, start making things like heavier elements that stars and planets and people are eventually formed out of. You've got the evolution of cosmic history here that all of astronomy is basically trying to figure out. And then you've got the present day here where we're actually looking back 13.7 billion years later. One other thing to notice is that the shape of this horn kind of contracts for a while and then it kind of goes out. And this about right here is when it stops. It's about 9 billion years after the Big Bang. And that's when dark energy becomes important. Dark energy actually is becoming more and more of an important thing in our universe, and that's where we went from decelerating to accelerating. So just one more look at this. We've got, this is basically just a list of all those things that happen between inflation and this period of atom formation where the universe becomes transparent and the cosmic microwave background is formed. One of the things to notice here is that we can potentially get through this, right? We said this is the oldest light we can look at from this epoch right here at 380,000 years. But there are ways that we're coming up with to potentially break through this and kind of explore what the universe was like earlier. One of them is the Large Hadron Collider in Switzerland that can get back to about this epoch or so. Right. Yeah. And then before that, potentially the polarization of the cosmic microwave background could tell us something about inflation. And I'll get into a little bit of that a little bit later. So the future of our universe. I was kind of struck by this. Lawrence Krauss published an article in Scientific American, which people may have seen. There was also a refereed literature version of this article as well. He basically ran the thought experiment, what's the universe going to be like in 60 billion years? And the idea then is that dark energy will have pushed all the galaxies in the Hubble Deep Field away, and we'd be stuck with this sort of local, gravitationally bound local group of galaxies. The cosmic microwave background will be much cooler, and maybe we wouldn't have been so excited about detecting it if we didn't know about Hubble expansion. So you actually do kind of return to effectively a static universe with a small number of island universes, which is kind of just an interesting thought that I thought I'd throw in here. So how do we solve the three outstanding mysteries in cosmology? We've got three of them, right? We've got inflation, we've got dark energy, and we've got dark matter. Well, it turns out that there really is no place like space. One of the things we want to do, like I mentioned before, is measure the polarization of the cosmic microwave background. Well, polarization in everyday life, of course, is has to do with the orientation of the electric field. Well, different physical processes actually have different polarizations, and that's why your sunglasses work well. Your polarized sunglasses cancel glare, and things look different in polarized light than they do in non-polarized light. So the approach here is to actually use polarized light to get to the inflationary signature that actually is produced by gravitational waves during the inflationary part of the period of the universe. So one of the things that to point out here, though, is that signal is really small. So if the isotropic cosmic microwave background is 2.7 Kelvin, the signature of inflation, which I've labeled B modes down here, is actually really tiny compared to that, 30 nanokelvin or so. So this is a challenging measurement, which is currently being attempted by the Planck observer. This is a joint ESA-NASA mission, and this is sort of the initial sky that Planck has put up on their webpage. And basically, they're going to try to put even better glasses on WMAP. They're going to try to measure the cosmic microwave background anisotropy to even more precise and more fine scale to see what kind of science they can get out of that. It'll also return some polarization data, which will be looking back for this signature of gravitational waves from inflation. And you can see here the blue and purple stuff here is actually our galaxy, and the cosmic microwave background is the stuff you see where the galaxy is really low. They actually are able to subtract most of this away. Beyond that, we anticipate a dedicated mission for studying inflation that will have more sensitivity and better systematic control than Planck. And if Planck discovers something about inflation, then this will be able to characterize it. If Planck doesn't, this will be able to potentially detect it. Another mission that's coming up that people are dreaming about is NASA Department of Energy Joint Dark Energy Mission, or JDEM. And this is basically a mission designed to map the history of dark energy. This is something we know very little about, and so the first approach is to find out exactly what it's doing. And no talk on cosmology would be complete without talking about the James Webb Space Telescope. This is the follow-on to the Hubble Space Telescope. Much larger mirror, operates more in the infrared, and this will be able to help us with cosmology as well as other observations. Specifically, this will be able to really tell us a whole lot about those first stars that formed after the Dark Ages. Not everything we do that will help with this puzzle will, of course, be from space. The Large Hadron Collider in Switzerland is likely to help out with dark matter. It's going to be able to explore an energy space further back in time in the Big Bang than any other particle accelerator to this point, and potentially could return some dark matter candidates. And so the interplay between high energy physics and cosmology will likely be increased. And this is just sort of an update as to where we are now. In the standard model of particle physics, we've got 6 quarks, 6 leptons, and 4 force carriers. There could be more stuff here as we explore higher energies. I put down here the Higgs boson. That's the particle that they expect to find in the Large Hadron Collider, and that's basically the particle which gives all these other things mass. But there could be other things that they find that as they go in higher energy. It's important to note that the standard model stops here potentially because we haven't looked anywhere else. We haven't been able to get any energies higher than this. And as we explore those energies, dark matter candidates could be possible to be discovered. So the goal here, as I start to wrap this up, is that we really want to go for a theory of everything. We really want one theory to describe our universe. That's really the aesthetic that we're going for, right? We've got all these partial theories. They fit together in a certain way, and we've seen this happen, right? We've seen Newton come up with a set of laws for motion, and Maxwell come up with a set of laws for electromagnetics. They didn't mesh, but Einstein was able to incorporate them both into his theories of relativity. The idea here that a theory of everything would incorporate the strong nuclear force, the electromagnetic theory, the weak force, and gravity all together. And that's likely to happen at a high energy. This energy is actually where those all come together is called the Planck scale. And the idea here is that as you go in higher energy, these things melt into sort of the same theory, right? They've already made a lot of progress in terms of the electromagnetic and weak forces merging into one theory. That's called the electroweak theory. This is something that is expected to occur on this scale. If they can find the Higgs boson, that goes a long way into cementing that branch of the chain. Inflation actually is expected to happen maybe somewhere around here. The energy scale for inflation could be something like the same that you expect from the strong and electroweak interactions being merged. So we've got some work to do, but it's fun work. And I'll leave you guys today with a thought. Around 1900, looking ahead to the 20th century, people expected physics to be quite boring. One famous physicist said he felt sorry for the next generation of physicists. It's easy to make fun of people in hindsight, but he basically said that he felt sorry for the next generation of physicists because all they would be doing is coming up with a few more numbers on the ends of these wonderful things that his generation did in the 19th century. There were a few things that were open, though. Something called the ultraviolet catastrophe. They didn't exactly understand how blackbody radiation worked. They didn't have a good theory for it, but they kind of said, well, we'll figure that out in the next few years, and one more person will have fun, but that's it. And then they couldn't actually find ether, which was what they were actually currently using to unify electromagnetics and Newton's laws. So there were these two things that were sort of nagging, but they figured they'd find ether eventually, and that this thing was not a big deal either. Instead, we got the 20th century as we knew it. So the people that they were feeling sorry for ended up being Einstein and Bohr and Feynman and all these people that did these wonderful things that pushed the bounds of human knowledge further than they'd ever been pushed and faster than they'd ever been pushed before. Because of the non-detection of ether, relativity ends up redefining the notions of space and time, ushering in an era of GPS and space navigation and all this wonderful stuff. The ultraviolet catastrophe led to the discovery of quantum mechanics, which revealed this microscopic universe that enabled all kinds of things: transistors, lasers, LCDs, atomic clocks, atomic energy, and a whole list of other things that are now on the table for the future generations to explore further. So, in sort of a stretched analogy, where we are now, we've got these outstanding questions. These are very cosmological-centered questions, but they certainly tie into fundamental physics, as I tried to say earlier. I don't think we have such weak expectations for this century and those coming. I think we're going to have a lot of surprises. I think it's going to be a lot of fun, and I look forward to the exploration. Like I said already, in my 15-year career in astrophysics, we've gone from wondering whether the universe was flat curved or whatever to wondering about dark energy and inflation. So it's rapid progress, and I suspect we'll have some fun seeing how it shakes down. Thank you very much for your time today, and have a safe trip home, and thank you once again for having me.
Are these slides available online somewhere?
I haven't made them available online. I could potentially give them to you.
Yeah,
if you'd
I'd
like.
love to have a copy.
Okay.
Just get a line.
Quick question. Hello?
Yes.
Quick question. Brian Greene, Fabric of the Cosmos. He describes dark matter as greater and larger as the distance between objects increases, I believe. Is that... Am I misunderstanding that, or is...
The one thing that actually increases as you increase distance is the strong nuclear force. Could he have been talking about that?
Well, he talks about that, but
okay,
I thought it was in relation to,
dark matter is believed to behave just like regular matter gravitationally. It's believed to be, well, I mean, because you need that to be able to suck in all this extra matter to create the structure we see, and that's
okay.
That's all, reduces the Newtonian limit of the 1/r² force.
Well, then maybe I'm not using the proper terminology. Would it be dark energy? Because if I'm understanding the description correctly, it acts in reverse.
Yes.
So it's dark energy.
Dark energy actually pushes things apart.
Correct.
That's right.
All right.
Absolutely.
I'm mislabeled. I'm not a technical.
No, fair enough. I totally understand it. There's a lot of dark things up here, and it's a little bit of our problem with not knowing what they are yet. But that's right. Dark energy is a really funny thing. We don't understand a lot about it. It could be that we're waiting for a big paradigm shift in thinking about these things, but that's exactly right. Dark energy actually is